Okay, so in the previous video that I made, we talked about a simple body connected with a spring, a cuboid kind of a body, which was displaced, and then we try to find the speed of oscillations and so on. And we ended the video talking about how things would change if instead of a cuboid, we now have a body which could rotate, something like a uniform cylinder or a sphere. And today, that's the focus of our video. So this problem from Iredov's book is actually very good to demonstrate that, where it's given that a uniform cylinder is kept on the ground, and there are two springs attached on the top, as you see in the diagram. And then the ends of these springs are attached to a wall, and then there is a small movement of the cylinder where it now starts to oscillate. And we need to assume that there is no slipping between the cylinder and the ground at the bottom point. Given this assumption, we need to find the time period of oscillations. So let's dive into this. First of all, in this sort of problem, it's interesting to note that if we move the cylinder by a certain distance, say x, let me draw it so it's clearer. So let's say this is the initial position of the sphere. And then I'm just exaggerating the scale here, but then this is the final position of the cylinder. Then assuming that this distance is x, right, and this is ground, where we are assuming there is no slippage, then the distance the center would have traveled, this particular point A, when it reaches here, there is an arc distance that it would have additionally covered because of the rotation, right? However, if there is no slipping, then this linear distance and the distance on the arc has to be the same. If it is not, then there is some sort of slipping that will happen, right? That the point on the surface is actually moved more than the center itself, which means that there is slipping. However, we have assumed here that there is no slipping, which means the distance on the arc on the top is also x, right? And this ensures that there is no slipping, which means the distance on the point A covers with respect to the ground. It's important to understand that distance is with respect to the ground is an addition of the simple movement on the straight line, which is x, because the whole body itself is displaced by x, plus the additional distance it went through on the top because of the rotation, which is again x, because there is no slipping, which means that the top point has moved by a distance of 2x, right? So this is important to understand. Again, if we were to say that this center moves with velocity v, there is a angular velocity omega, radius is given. For no slipping, we also know that v is equal to r omega, right? We can derive it very easily as a condition of pure rolling or no slipping. So with that in mind, let me just get rid of this diagram and let's dive into solving this. As we discussed in the last video, typically it's easy to look at these problems in terms of energy conservation. We know that initially the energy of the system is zero when it is at rest, but finally there are two springs that are involved here. Assume they have a spring constant of k1 and k2. We know that the displacement of one spring or the compression of one string is the extension of the other one because it's a linear setup. So we know there are two potential energies involved here. So let's just write it out as half k1 x square plus half k2 x square. We also know that there is linear motion. The center moves with velocity v, so there is a kinetic energy. However, there is also a rotational energy here, which is given by half I omega square. And for a uniform cylinder, we already know that the term I is given by mr squared by 2. I'm not discussing how it comes across, but let me know if you want to learn more about it. But it's fairly simple to derive that. So we're going to assume that here I is given as mr squared by 2 for a uniform cylinder. We know, as we discussed earlier, that v is equal to r omega, right? We also know that for a simple harmonic motion, acceleration plus omega square x equal to 0. How do we get this equation? It's actually simple, and I'm not going to derive it here, but we know that force is equal to minus kx for spring systems, and force in itself is mass times acceleration. So you could transfer the kx to the other side, and we know that because of the sinusoidal nature of spring oscillations, there is omega square term. So we can take this as a given condition for this problem again, that if it's a simple oscillation, we assume that the acceleration of the system, center of mass plus omega square x, is 0, right? And then, of course, with energy conservation, we know that initial energy is final energy. So given all of these conditions, we can go ahead and start solving this. Let's just simplify the energy, the final energy of the system, where we say that half here, assuming that the center of the cylinder has moved by distance x, actual compression for the string, as we derived earlier, is going to be 2x, right? So that extension is going to remain constant, and then I say k1 plus k2 here. I also know that the half mv squared terms remain. However, I can simplify the I omega square using these equations, where we say that as mr squared by 2, and then the omega can be replaced by v square by r square, where the r square gets cancelled, which implies that, and I know that k1 plus k2 has been given as xi, right? So we now know that 2 times xi x square plus, there's a half mv square here, there is a 1 by 4 mv square here, so overall it's going to be 3 by 4 mv square equal to 0, right? And now we know that if we are able to get to this form of equation for the simple oscillation, where the acceleration and the displacement is there, we can directly find out the omega, and we know from there on that time period is simply given by 2 pi by omega, right? So the goal here would be to convert this equation, which has a velocity term, which has a x squared term, to somehow with an equation having a and x. And if velocity is given, how do we get to acceleration? We just differentiate it with respect to time, right? So let me just rearrange this equation for better clarity, where the acceleration term can appear first. And now I'm going to differentiate this whole equation with respect to time, which implies that 3 by 4 into 2 mv dv by dt plus 2 xi into 2x dx by dt equal to 0, right? We also know that this term, dx by dt, would be the velocity of the center, right? So this velocity and this dx by dt is going to get cancelled, okay? So we can just say that it's 3 by 2 m times a, because this term is now dv by dt, which is acceleration, plus 4 xi x equal to 0, or we can write it as a plus 8 xi by 3m x equal to 0, right? We now know that this is comparable to the equation a plus omega square x equal to 0. So we can directly find out that omega is root over 8 xi by 3m which implies that t is given by 2 pi by omega, which is 2 pi root over 3m by 8 psi. And this is the time period for the oscillation of this system. Right? In fact, there's a better way or even easier way to look at this problem, where we think that how can we convert this rotating cylinder into a simple mass which is not undergoing any rotation, and we can find out what the effective mass of that system would be if we combine the kinetic energy and the rotational energy and try to find the effective mass of the system, which we can think of as doing a linear oscillation. And then we can also similarly think of a combined k effective of the system and just go from there, because time period is given also by 2 pi root over mass effective by k effective of the system. So it's a very cool trick. Maybe it's faster to solve that way as well. So let me know if you're interested to explore that route of solving this problem. But until then, this is it for this video. Let me know if this was interesting or if you want to discuss something more on this. Otherwise, we'll keep coming back with more interesting problems in the next one. Until then, keep working on your concept and I'll see you in the next one. Thank you.